Okay, so let's assume that again that we have so this here is a sequence. Then we can form from a sequence. We can form another sequence. So from AN we can form another sequence. At least if AN is bounded from above. So we can form another sequence, and that's what we take. Bn is going to be the sup of the set of A starting at n. So this here is this here is the sequence Bn. Okay. And so, right again, implicitly here we are assuming. So assume that there exists some C, so that for all n, AN is less than C. In other words, the C are bounded from above. Right? So if the sequence AN is bounded from above, then this here gives us a real number, and we see that since if you're looking at Bn plus 1, this is now sup of AN plus 1, AN plus 2, and this here is sup over a smaller set. So this here is less than the sup where we do it over, where we take sup over a larger set, right? And that here is Bn. So we have that if you take any sequence, then you can, and let's say that sequence is bounded from above, then you can find another, you can form another sequence Bn, and Bn here is monotone decreasing, right? If the sequence Bn is bounded from below, then the Bn here, in the sequence here, converge, and it converges to the infimum, right? This is with monotone convergent sequences, it's converging to the infimum of the BIs. Like that. Okay? Now, and likewise, although we won't really use this here, so likewise, again, if AN is any sequence, this time I want it to be bounded from below. Then you can find a sequence, then you can form from AN, you can form a sequence CN, and CN is just where you're taking the infimum starting at AN. Right? And you see that if you're looking at Cn plus 1, then you take the infimum over a smaller set. So this is a smaller set, and so this here is bigger than where you're taking the infimum from AN. and that's Cn. So the sequence Cn is therefore monotone, increasing, and if it is bounded, so if Cn is bounded from above, then the sequence Cn converge to some C, and that C is just a soup of the C's, right? And so, and we talked a little bit about this earlier, right? And the thing is that, but now we will use it in just a second. The thing is so that in the first case here, we call B here. B is written as the Lehm soup of the AN. And in the second case, it's called the Lehm inf of the AN. Okay. Now, so why is this relevant here for us? So what we were looking at last time, and I'm only going to use the Lehm soup. So last time we had a sequence, so AN is a sequence, or was a sequence. And we defined what we call a power series. And again, power series, think about that X as being just some fixed number. And you have the sequence AN, X is some fixed number, and then you form the sequence AN XN, right? And so for each X fixed, this gives you some number, maybe, if it's converge. I mean, you can ask for each X, you can ask, does this sequence converge or not? And this here is called a power series. So you're summing from 0 to whatever, or you're starting from 1, or whatever you're starting with, up to infinity. So this here is a power series. And so now, for a power series, the question is, power series is, the question is, what about, for which X does it converge? Okay, so that's what we're interested in. And what we looked at last time, so just let me remind you, because we're going to use that anyway in a minute. Last time, so example from last time. Well, the example we looked at last time was, we're looking at xn. I mean, we looked at some other examples too, but this was the one we focused on. So this here is a power series. The AN in this case here are 1 over n factorial. Right? So now, and for each fixed x, so for x fixed, we looked at whether or not this sequence converge. And so we think about this thing here. We thought about it as just a sequence like this, sum of a sequence. So this is as a series like this, where the dn here is now x to the n over n factorial, right? And so in order to determine for which x it converge, so just think about x as being fixed, we use the ratio test. So we use the ratio test, and the ratio test said that if you're looking at dn plus 1 over dn, this here is, well, dn is just x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. And that's the same right? So when you divide by a fraction, you just switch, right? So this is the same as x to the n plus 1 divided by n plus 1 factorial times n factorial times x to the n. And you just think about this, the top here, as x to the n times x times n factorial, and the denominator you think about as n plus 1 times n factorial times x to the n. And you see that this here and this here cancel with those two. And so you get x over n plus 1. And this here converts to 0. Right? So therefore, the power series is convergent for all x. Right? Now, so that was a particular example of a power series, right? But so and it worked well with the ratio test. But the root test actually is better, and this was related to a point somebody raised last time, and the point was like, like for the ratio test, it was, implicitly somehow in the ratio test was something about that from some stage on, the next element is smaller than the previous one. And you don't really need to have that. You certainly don't need it for a series to converge, but it's not even necessary if you apply the right test. Right? And so this brings us to what's called the radius of convergence. So this is a crucial concept, and by this crucial concept, because you see a priori what you could imagine. So suppose you just write down a power series like this, right? A priori, maybe like that it's convergent when x is equal to 5, it's divergent when x is equal to 10, and maybe it's convergent again if x is equal to 20, right? That's not actually going to be the case. So there's something called radius of convergence. And the radius of convergence and the thing is that what you get out of this radius of convergence is that a power series like this is convergent on some interval, and then outside this interval is divergent. So it's not like you have some that is convergent here, it's divergent there, and then it's like convergent again, right? That's not what's going to happen, okay? Part of this is also, we already saw this in the different tests, that there is at the boundary of this interval, the test is inconclusive. So you have to check the boundaries separately, okay? And so the idea is that you have a power series like this, and you think about, again, you're thinking about dn as x to the n. X again is thought of being fixed. And now you apply the root test. So apply the root test, but I'm going to apply it in a better form than what we did last time. Maybe I'll just state first the better form of the root test. So here's the sort of, here's the real version of the root test. So suppose you take a series. Suppose you have some series here. Let's call it dn. Suppose you take a series like this. If you're looking at, so now the root test, right? You took dn, you took the absolute value, and you took the nth root, right? When I looked at the root test last time, we looked at whether this is convergent or not, right? So we said if it was converging to something, right? But you could just you could form this thing here. So you could form from this here, you could form this. This is now a sequence. And you could look at Lim sup of this. These here are all non-negative numbers, right? And this Lim sup here is now going to be either infinite or it's going to be some real non-negative number, right? This here is going to be infinite. Usually we don't talk about that it's converging if it's infinite, or it's some number. Let's call it D, I guess. But okay. And the thing is that if you're looking at, if you set R equal to 1 over D, right, sorry, no, if you're setting, so this is just the root test, the sort of adult version of the root test, because this applies to all sequences, right? For any sequence, you have this. For any sequence Dn, if you're looking at this series, you can look at this, right? And it's either infinity or D. And then if D here is less than 1, then the series is convergent. If D is bigger than 1, the series is divergent. And if D is equal to 1, it's inconclusive. Right? The difference between this and what we talked about last time was that last time we assumed that this thing here converge. Here I'm not assuming it, but then I'm looking at the Lim sup instead. Right? So this does give us a number. Okay, and it's just a matter of whether the Lim sup is smaller than 1, and then it's convergent, or bigger than 1, then it's divergent. Okay. Now I'll come back to the proof, but the proof is really kind of the same as the one we gave. The one we gave really, if you kind of mimic what we did in the special case last time, then the proof would still apply to this case here and give this result. Okay, so now, but let's take this more fancy version of the root test. Let's take that for granted. And so now I have a power series like this. I just for clarity, I define Dn to be just An times Xn, and I'm interested in is for what x does it converge? Does the power series converge? Okay, now, so now you see that, so Lim sup, so you were looking at Lim sup of the nth root of Dn is An times Xn, and you take the absolute value of that, right? That's what you're looking at, and you're asking, is this smaller than 1 or bigger than 1? But this thing here, right, this is the same as Lim sup, right? If you're looking at this thing here, let's do a little side calculation. If you're looking at the nth root of An times Xn, this thing here is the same as the nth root of this product here. Absolute value is the same as this times X absolute value to the nth. And when you take the nth root, you may as well take the nth root of each of those two factors individually. So this is what you get. But this thing here, you see this thing here, the end root, this here is whatever it is. Can't do much about that. But this thing here, that's just the norm of x. Right? The norm of x has the property that when you raise it to the n power, you're getting this. Right? So this is the n. Okay, so this means that this thing here is the same as the norm of x lim sup of the nth root of an. Right? Often you do it like this. You don't have to do this. It's usually clear anyway, but often you write it like that. Okay, so now what you do is, so you're asking, when is this number here smaller than 1? When is it bigger than 1, right? And so you have that, you see now you define something that's called the radius of convergence. And so this is the following. So the radius of convergence is, radius of convergence is, so this is just radius of convergence. The radius of convergence is just a number. And that number is radius of convergence. And we have to just interpret it a little bit. So it's 1 over lim sup of the nth root. This thing here could, of course, be infinite. If this here is infinite, then the radius, by definition, this here would be 0. Right? Right? Where this here is equal to 0 if this lim sup is infinite. And otherwise, right, it's always a, right, otherwise, yeah, there's one other case you have to define, that if it's infinite, if the lim sup, sorry, this should be absolute value, if this lim sup is 0. And otherwise it's a, otherwise there's nothing to, it's a, that's the only thing you have to comment, right? Because otherwise it's always a non-negative number, but it could be 0 or it could be infinity. But if it's any other number, then it is just what you think it should be, is 1 over that number. Okay, so this gives you, this here, R here is the radius of convergence, okay? And now the thing is that now we have the following simple picture. So now we have that, so you have this power series. Again, it doesn't matter what you start with. The sum matters what you start with, but not the convergence. So you have this power series. You are forming R. This is the radius of convergence. And then the claim is, and again, this could be 0 or it could be infinity, but often it's just a real number, a non-negative real number, a positive real number. And so it says that if you take the interval here around 0, in the interval from minus R to R, then inside this interval here, inside here, when x is in here, then the power series is convergent. And when x is here, or here, power series is divergent. And then when x is here or here, at those 2 points, then it's unclear. And further test is needed. Further test is needed. Tests are needed. Okay? Yep. Yeah, so that's right. So let's come to the proof. Yeah, so this is what you're talking about. So this is the radius of convergence, right? And so as you say, all we need to do is, right, we know from the more fancy version of the ratio test that is in terms of leap soup, we know that, so prove here, power series is convergent by the ratio test, by the ratio test. Not the ratio test, sorry, the root test. By the root test. So again, the leap soup version. Not the one I talked about last time, but this one we just talked about. By the leap soup version of the root test. Then the power series is convergent if this thing here, so this means that this thing here, so if this thing here, leap soup of an nth root, if this thing here is less than 1, it's divergent. If this thing here is bigger than 1, and it's inconclusive, and it's inconclusive if this thing here is equal to 1. Here it's inconclusive. But now you see that this here just means that the norm of x should be smaller than 1 over that, right? So this here is the same as saying that the norm of x is smaller than r, the radius of convergence, right? This here is saying, this is equivalent to saying that the norm of x is bigger than r, right? And this here is equivalent to saying that the norm of x is equal to r. Right? Okay, so that's a radius of convergence. So you see. So this is like, a priori, this is not at all clear that it couldn't be, that a power series couldn't be convergent for like, some sort of discrete set of x, but that's not the case, right? It's convergent on some interval. It's unclear at the end of that interval, but it is convergence on an interval and divergent outside that interval. Now that interval could be just 0. Or it could be all of R, right? But it is also symmetric around 0. Yeah.
But when we bring that over, isn't it
yep.
1 over?
Right. So it's 1 over this here. But remember how R was defined. R is up there. Yeah. Okay. Now, let me just say a word about why does the proof from last time, why does it really prove this more, the sort of argument we gave last time, why does it give you this much more, this much more satisfying, this version of the root test, because it applied to any series. Right? Because otherwise we talk about whether some ratio was convergent, but it may not converge, right? So this is much more satisfying. So suppose again you have a series like this, and so now you're looking at leap soup. So this here is, again, this is the root test version. Let's call it version 2.0. Right, and so it take a series like this, and it's it's looking at Lim sup, and then the nth root of the absolute value of dn. And again, it say that if this thing here is less than 1, it's convergent. If it's bigger than 1, it's divergent. And if it's equal to 1, it's inconclusive. Okay. Now let's try to see why this here is the case. So proof of root test version 2.0. So now, maybe I won't do all of it, but let's just look at, because you see in a minute, you see that it's really kind of super similar to last time. So suppose that this limit, suppose that this Lim sup of the nth root here, of dn, suppose that this thing here is equal to some d, which is strictly less than 1. Okay? So this means that there exist, so choose, if you will, choose d bar with d less than d bar, strictly less than 1. Right? So I can choose it like this. But now you see that if I choose it like this, then there exist. So remember that, let's just remind ourselves that how was the Lim sup defined? The Lim sup was defined to be that you take this new sequence, so you're taking this sequence here, so you're taking these guys here. So you're looking at now these guys here, and you are taking you define a sequence that is like the sup starting at the nth guy and like this here. Sorry, this here is n plus 1, etc. Right? Right? This is the sup of the tail, right? And so that it was sup on, as you're going further out, you're taking sup over smaller sets, so this sequence going down, right? So now if this limit here is some d, which is strictly less than d bar, then it means that there exist, capital N, so that if little n is bigger than capital N, then all of these guys here is less than d bar, right? So this here is, so if this here, then all of these guys here is less or equal to d bar. This is if little n, if you're starting that far out, right? But so now you see that, so you have that when n is bigger than this, you have that this, so you have that for all these guys here, dn, the nth root, is less than d bar, less or equal to d bar. But now you take the nth root, the nth power on both sides, so you have that dn absolute value is less than d bar, the n power. This here is d this is even actually non-negative, so you don't even need this absolute value sign. So you're having this, but this is a number that is strictly less than 1. So this here is a geometric series, right? Geometric series. With where d bar is less than 1. So it is a convergent geometric series.